Hey, this video is about molecular shapes. Molecular shapes are things that we look at the actual three-dimensional geometry of covalent compounds. We only do this with covalent. With ionics, they form crystals, and there's a lot more that you can learn about the shapes of the crystals too, but we're going to focus on covalent compounds. And the shape of the molecule has everything to do with the chemistry of why it does what it does. So if you take more biochemistry, or if we get to organic chemistry or pharmacology, those kind of things, the molecule shape has everything to do with how it works, like a medicine. Even the way that our proteins and things fold within our the structure has to do with this. So we're just going to teach you the basics though. And the theory that we use is, we call it VSEPR, even though it doesn't really spell that way, but it stands for valence, which are those outer electrons. So valence shell electron are the outermost valence electrons, and they're in pairs, and they repel one another. And then that gives us, when they repel, they take up as much space as they can, and that gives us the shapes. So let me show you. So there's a FET that's really good. So this will be, the purple is like the central atom. And if I add, just one atom, it's not that exciting. They're just going to be 180 degrees apart. Another, same thing. So if I were to kind of try to bend, so the stick part here is a pair of electrons. It's a single covalent bond. If I try to bend those electrons towards one another, it always kind of bends back. As I add more, so you can see there, it kind of pushed these down when I added that one. I'll let you see it again. And you can see this is three-dimensional. So the space between them, is optimized by this angle, which is 120 degrees. Here, I'll show you the bond angles. So if I were to add another, see how the bond angle went down even more so. So these electrons, two electrons in these bonds, which are kind of like a stick in this kind of a simulation, they are repelling one another and causing this to take on the shape. So hybrid orbitals are when two or more different orbitals will actually combine and form a new type of orbital. Don't worry, you don't need to have to be able to draw the electron configuration or the shapes of these, but it's pretty cool. So, for example, you know how I taught you to draw carbon's electron dot structure? I told you that you should go 12, 3, 6, 9, and then double. That's because of hybridization. I just didn't tell you at the time. So carbon has an electron configuration of 1s2, 2s2, and then the 2p2. Which would make it look like, would we bond, it's usually the unpaired electrons that'll then pair up. So it looks like carbon would only bond 2 times, but in reality it bonds 4 times. And you can see that when you look at the electron dot structure. So by undergoing hybridization, it allows carbon to promote one of these electrons into the p, and then they kind of morph into these equal energy orbitals, which we call Sp3. And that allows carbon to be able to bond enough to get an octet of electrons. So this is what it would look like before bonding, but then when it's ready to bond, and it does bond, these orbitals are going to morph with these orbitals. And they're actually going to have an in-between amount of energy. You don't have to draw this, I just want to show you. So when I say Sp3 hybridization, it's really an Sp3, all equal energy orbitals, and this is what it would look like with those 4 valence electrons, 1 in each orbital. So then carbon can bond 4 times and end up with 8 valence electrons. The actual shape of the orbitals, you know, the sphere and then the dumbbells, that actually morphs together too. So you end up with this kind of combination of the two orbitals. I like this. This is a really good way to show it. So the Sp3, you know, they're kind of dumbbell, they're kind of partially sphere. And again, you don't have to be able to draw this. I'm just trying to show you just that the orbitals themselves actually combine and form kind of a hybrid, which is a different sublevel shape, and then that allows for the bonding. So this is the sheet you should have out or have printed or write this in your notes. So you could pause the video and just sketch this into your notes. You'd probably want to give yourself about a full page for this drawing. And then when you're ready, start the video. So I'm just going to go through these with you one at a time. So first, we're talking about Sp3 hybridization, what I was just showing you. So we would have 4 equal energy orbitals. So one thing that we can have is, and I'm going to use the letter A just to show some element. You don't know exactly what it is, and we're going to call that the central atom, the one that's in the middle. And then you would have those X, another type of atom going around. So this is one type, and we call this shape tetrahedral. And I'll show you on the PHET, the one that, like this would be tetrahedral. So if there's 4 bonds, there's no lone pair electrons around the central atom. We're going to deal with some that do. And let me just keep going with you. So, an example of this would be carbon likes to do this. So let's say you have carbon bonded, and it's hard to show, you know, it's not really 3-dimensional on paper, it's flat, but realize that it really does look like this, where 2 of these would be chlorines and 2 of these would be hydrogen. And you can see the angle is 109.5, and we'll see how that changes too. So this angle is 109.5. Our Lewis structures would still have those electrons. So now we're going to look at this part of the chart. So around the central atom, there are 4 bonds. See, 1, 2, 3, 4. And there are no non-bonds. There's no what we call lone pair electrons. There's also a notation called the ABE notation, where A is the central atom, so you'll always have an A. B is the number of bonds, so in this case it would be B4. And then there is no E because this would be E, and there aren't any unbonded electrons. And then we're going to leave this column till later when we cover a different concept, but leave that in your notes open because you'll want to go back. So let me show you another type of Sp3 hybridization. It's going to be, the next shape that we're going to cover is also Sp3 hybridization. So you're going to have 4 bonding areas, 1, 2, 3 bonds this time, but we're going to not have a 4th bond, but those electrons are going to be unbonded around the central atom. Those are called lone pair electrons. And notice how they kind of bent the shape. Like if I take them out, but then once I add them, those electrons are very negative. Because they're not being bonded, they're especially negative, and they're pushing down on these other, causing this shape. So if we go to our sheet, I'm going to do this with you, we would still have a central atom we'll call A, and then we would have those 3 bonds and that lone pair of electrons. You can leave them like that. You can put a little bubble around them the way the PHET did. So an example of this would be NH3. This is ammonia. It's a cleaner that is kind of stinky. And you can see that it has 1, 2, 3 bonds. And now it has 1 lone pair. So notice these add still to 4, which is its S. Consider that 1 plus those 3 for a total of 4 orbitals or 4 bonding areas. This one also added to 4. So this would be ABE notation would be AB3 because there's 3 bonds. A is the central atom, and then E1. So let's look at the next one that has Sp3 hybridization. And this one is still going to have those 4 areas. 1, 2 are bonds, but 2 are going to be lone pairs. So you can see these lone pair electrons really have an effect on repelling these other electrons. So they're very negative, and they cause this molecule to really bend. We call that bent. So back to our notes. So bent is going to, and we're not going to even try to draw it, the shape of it. We're just going to draw it, well, I guess for this one you could if you wanted to try to kind of bend it down. And then you have those 2 lone pair electrons on the central atom. So an example of this is water. I'm just going to draw it straight across, even though it is bent, because it's really hard on paper to show it anyways. So you can see around the central atom, which is oxygen, there's 2 bonds, there's 2 lone pairs. So our ABE notation would be AB2, 2 bonds, E2. Okay, one more type of tetrahedral or Sp3 hybridization is if you have just 1 bond, but the central atom still has 3 lone pairs. So it really still has a total of 4 bonding areas, 1 bond, and then 2, 3, 4 other areas that aren't bonded. So we would draw A, and then the other, element, and A would have those 3, if we want to draw them as bubbles, you can. 3 lone pairs and 1 bond. An example of this is where hydrogen fluoride, the fluoride is the one that would be the central atom, has 1 bond, and it has 3 lone pairs. This still adds to 4, so does this one. So we know we're talking about Sp3 hybridization, or an electron geometry domain of tetrahedral. So this is another way of saying it's Sp3. So our ABE notation would be AB1, E3. And the shape is linear. So back to the PHET, it's definitely going to be in a line. So this is considered a linear shape.